Good morning and welcome to our final webinar of our training program, Renovation and Thermal Modernization of Historic Buildings in Times of Climate Crisis. I'm your host, Aleksandar Jelovac, and we are very close to the finish line of our one-month program. At the end of today's webinar, I will discuss what happens next after our program finishes. So what will going to be the next steps? Until when will you have the access to the Moodle platform? What are the exact dates for the city workshops? And when will you receive your grades for your assignments? Today we have one speaker, Mr. Juraj Pojatina. Our second speaker was supposed to be Mr. Tomasz Jelensky, but unfortunately due to some private matter, he had to withdraw at the last moment. If there will be a chance, Mr. Jelensky will record his presentation, so we will upload it to the Moodle and make it available for you. As always, please use the chat box and the question and answer section to ask your question. And at the end of his presentation, Mr. Pojatina will answer them. So allow me to briefly introduce Mr. Pojatina from the studio Arching. His area of specialization is engineering wooden and steel structure, seismic analysis, and rehabilitation of historic buildings. Among the most important professional improvements are the design of composite wood concrete structure in Lindau, Germany, and in the field of static reinforcement techniques of old buildings in Barcelona. He is a certified building seismic assessor for the US Department of State of Foreign Affairs. So I'm very pleased to introduce Mr. Pojatina, and the floor is yours. You may share your screen and begin with your presentation.
Okay, thank you, Alexander. I'm very pleased that I can share my knowledge and experience. This is the structural engineering aspect of the renovation of heritage and old buildings. I'm going to show you several projects and buildings. Some of them are already finished. Some of them are in design phase, but the main target and objective for me is to show the way one should approach the heritage building, assess it, and then plan the retrofitting measures. As I was introduced, I finished civil engineering faculty in Zagreb, University of Zagreb. Had my several education regarding heritage buildings. I'm working for also US government as a building seismic assessment expert. And also I have 20 years experience in designing both heritage and new buildings, but this assessment, refurbishment, renovation measures are my specialty. So as I already announced, these are some specific issues in structural assessment and the intervention approach. We have the most used and the hype word is an interdisciplinary approach. This is very modern today to talk about it, but this is the real truth. So we have a very wide range of involved competencies: engineers, architects, material experts, conservators, restorers, art historians, archaeologists, lab technicians, and this is all heritage buildings throughout the world have the same team who should be approaching them and design renovation itself. Very important for me personally is historical information. Some buildings have very thorough and rich archives held by the owner or conservatory department, and some buildings do not have nothing. So this is the huge part of research that engineers should do. Apart from this historical research, we have to do investigative field research throughout the whole of materials in order to understand the structure, to see the damages, to see cracks, to see what is going on. And then as a last step, we do structural analysis, some numerical modeling to confirm, to confirm our presumptions. So identification of potential vulnerabilities in order to understand the structure behavior. And then as a last step is intervention design. Therefore, I wanted to emphasize this. So when it comes to heritage building structural interventions, a thorough assessment is everything. The retrofitting measures just follow. So again, this is very important for each structural engineer. We have a very today huge a variety of different computer programs, and which helps us, but we shouldn't forget the field research. We shouldn't forget investigative part. We shouldn't forget in situ testings, and all of these activities helps us to understand the structure. And then, as here is stated, the measures just follow. So let us begin with this 19th century public building. The majority of presented buildings are in Zagreb area. Some of them have been seriously damaged by this by 2 earthquakes we had, and some of them were repaired before. This building consists of 2 parts. I hope you can see my pen. Okay, so this is the first part, and this is the second part of the building. The owner is the same, so we have to analyze it separately because in the joint here we have 2 separate walls. First, as I already said, the investigative parts, these are some characteristic drills and sondage and testings in order to find out what is inside the walls, what is inside the floors. And this helps us to understand the structure, the behavior, so we can plan. This is the characteristic floor plan. As you can see, again, I'm going to discuss only structural matters. So but I hope it will be interesting for the other listeners, also architects or other listeners. So as the plan shows us the weakness of this building, and this is the lack of walls in transversal direction. So this is direction which does not have enough seismic walls. All walls here you can see are only partition walls and do not work in the seismic loading. So longitudinal direction is good because we have 3 very strong line of walls. In the front is the street, and at the back is some kind of backyard. This is the downtown Zagreb. These buildings are in a block, so we are very much free to do at the back whatever we want, just as long as we do not interfere with the street wall. Also, these are our concept design of the seismic strengthening. So the black lines are new walls. These walls are going to be reinforced concrete, and they are easy to interpolate. So we have several walls here, and we have 2 very strong and powerful new cores down here. The main challenge is to attach this front part of the building to the new strengthened core, and I will show you how it was done. So this is masonry building with timber floors. This sketch shows us the main weakness of this type of buildings, and these are these joints here. Among a huge number of buildings, this connection is horizontally unconnected between timber floors and wall, and therefore during earthquake we have this kind of behavior of walls, and usually the damages and cracking and those kind of buildings are like so. The majority of cracks are here, and near ground floor is almost nothing. This is because this red lines shows us that these walls are free out of plane, so we want to connect them to the floor slabs. After this connection, this is the box-like behavior we want to achieve. This type of behavior have a totally different type of damage. The majority of cracks are here, and some here. on the upper floors, almost nothing. But this building, when it's properly connected, is much more has much more seismic capacity. So these are the measures we planned to do. This black lines present steel ropes, pre-stressed steel ropes, in order to attach the front of the house to the new strengthened cores in the back. So these are the pre-stressed steel tendons, and the blue lines presents steel elements like angle profiles in order to achieve floor diaphragms to stiffen the floor in its own plane. So the yellow lines are reinforced concrete, as I said, in the back, and also here at the joints, and here. So we have this symmetrical new disposition of elements, and therefore the building is much more stronger. These are details. These methods are very subtle. They are not so invasive. Therefore, we do not touch the floor layers. We do everything here under ceiling, only under ceiling, so the floors can be remained untacked. This detail here shows us these are two steel ties afterwards pre-stressed. Here are some photos from the construction site. These vertical steel rods are geotechnical anchors, 12 meters deep, in order to have tension forces at the bottom of the new core. And this is rebars for a new wall. Also here you can see this steel angle here, which is under the ceiling, and this here is a partition wall, and the very important thing is for this steel angle to have continuity. So we had to break this partition wall in some small area just to have continuity of this steel angle. These two guys are pre-stressing steel ropes from the outside, and we achieved approximately 2.5 to 3 tons per one steel rope. Okay, second object is very famous Viewpoint tower in Zagreb, Park Maksimir. This is the masonry structure, early 20th century. We have original archive drawings. As you can see, this is all bricks without concrete or without steel. Therefore, during this earthquake, it had a huge number of damages and cracks in this area here. So in this section here, the building is the weakest because it doesn't have enough walls to transfer the horizontal force. Therefore, since we have this cape around it, we have also the stiffness, the stiffness issue here. So our so this is the basic mechanism, damage mechanism. We figure it out. So when we look at the majority of cracks, so this is the most vulnerable area, and therefore with the measures we want to strengthen this part. Again, all the measures are going to be inside and not the outside to ruin the appearance. So so this is the steel, like it's like steel cape from the inside, which is modeled as a fear and deal girder. It's like a truss, but without diagonals. Here we have chords. This one, this angle profile is a chord, and these are horizontal elements. Again, we have steel ropes from the inside for the pre-stressing, and this is the detail, anchorage detail from the outside. It will be covered in plaster afterwards. So as you can see, we did not anchored this system to the foundation level. We just put it in the terrain level, because the forces, the horizontal force is like so the moment it creates with this tower, this cantilever. So this is the section with the maximal horizontal forces. Okay, let's move on to the next. It's a church tower, 18th century. This is the stone masonry building. So these are investigative openings. These are the cracks we discovered. This crack here is the most important. We'll see it afterwards, and it is the most severe damage here. So we did the numerical modeling. This is the linear approach, and this is the nonlinear numerical modeling, which helps us to understand why this crack was formed. So this is the one. It goes from the church like so to the other part of the tower. And this is the mechanism we discovered as the most effective one. So if the earthquake was any stronger or more lasting, the possible collapse would be like so, because also we have this kind of this kind of deformation of the tower. So there is a evident sliding slope sliding plane that was created here, and this is what we have to prevent in the future. Therefore, we plan to make this shear insert just to prevent any to transfer this horizontal shear force. And these are two solutions. Of course, inside of the tower, we can do our measures, and the outside interventions are not likely to be accepted by conservators and architects, and so this is the two solutions we introduced to the conservatory department and to the owner. So this steel truss, this one was selected. Again, as the tower shown before, this is the like steel tube inside, but with real truss with diagonals. This is the reinforced concrete version, but this is very invasive method, and therefore this solution number one was shown and accepted. So these are drawings, the main and detailed design. We attached church to the tower because the church itself is very weak, and in this level of the tower is very strong and powerful in a way of shear force transmission. So we put two rows of again pre-stressed steel ties, and this here is the steel truss as numerical model. So it works with the stone masonry. Also, this lower part of the stone masonry will be injected with some cementitious materials in order to improve the shear capacity of the tower. Okay, let's go further. This is the 18th century castle. This is important. I wanted to show it because of the damage mechanism which occurred. And once you found out what this damage mechanism is, you can very easily intervene. So this is the plan, and this is the 3D calculation model. These red dots are damage which was evidented after the earthquake. So this is just to illustrate the way we show these cracks, so you can easily track down possible local or global mechanism which took place. These are again investigative works and drills. So this is the one typical cross section of the wall. The lower parts of the castle is stone masonry with the infill here, like so, and stone elements at the face of the walls. Also, this is endoscopic investigation of the walls. This is the most the biggest deformation area of the walls, perimeteral walls we found out. This is the 3D scanning of the deformation. So there is a huge out of plane displacement of this wall here. And this is a sketch in order to understand what happened. So this last field of these masonry arches is pushing the walls outside, and therefore there was a crack within the transversal wall, which was here to prevent it, but after the cracking, the displacement was around 20 centimeters in the last couple of decades. These movements are very slow and long-term. So this historical part of investigation is also very important. Sometimes is very useful to talk to the people who live in the building or around the building, especially older people who have memories of the events that are not archived or cannot be found in the archives or plans. Again, this is the same mechanism shown in the plan view. This wall here have serious cracks here. So because this horizontal force is very strong, and therefore this wall came out. Also, this room here have a very large displacement of the walls, who are going again out of plane to the inside. And afterwards, it is very easy to plan the measures. This is the emergency measure. This is not a permanent solution, but because the castle is the hospital, and therefore none of the construction work can be provided from the inside. So we designed this kind of support, temporary support structure from the outside. So in order to prevent this type of out of plane displacement. Again, this is the hole from the inside with the steel rods, which attach again this wall to the longitudinal ones. Also, another 19th century church with the tower damages, and also masonry dome damages. So the tower is masonry, brick masonry. It is 18th century masonry, which was afterwards in the early 20th century was upgraded to the today's level. So this red hatching is are the zones, critical zones with the most of the damage. Again, the stiffness, changing stiffness here. Also, huge number of windows here. Here are also the belts with the mass concentration, and therefore the majority of cracks are found here. So how are we going to strengthen it? We again do not interfere with the outside perimeter wall face of the walls, but only from the inside. And inside, due to the tower height and the very intensive seismic forces, we had to plan this reinforced concrete core from the inside, not to just to hide it and not to interfere with the outside appearance. So this is the concept design. Those two rooms or volumes are used for this load transfer to the outside perimeter walls. It is like I put here this catamaran, a sailing boat, because this is the same principle. Those parts members here helps us. These are here. When we have an earthquake in this direction. In the perpendicular direction, the core itself should be enough. Again, as I said, there are very serious cracks and deformations in the masonry dome inside. These red lines are cracks, so they are showing us that the outside, these outside perimeter walls are going out. So the dome is losing its bearing plane, its bearing points, and therefore this is the damage mechanism and possibly the collapse mechanism which is going to occur for more serious earthquakes. Again, as I said, this is the cross section, so the autoplane deformation of longitudinal walls causing instability of the masonry dome. So intervention concept is to have closed steel tension ring from the extrados of the dome, and none of it will be visible from the inside. Again, this is only these blue tension ring elements are at the extrados of the dome. Black steel lines are steel bands, again on the dome extrados. So this is the way to embrace these horizontal forces and to get them back to the dome and not to push outside walls like so. So these forces remain here in this tension ring and do not going outside, causing autoplane deformation of the walls. some different problematics with again with church towers. This is near Petrinja area, again old church tower with which has primarily issues with foundation soil instability. Here is a slope like so. So this is the possible sliding mechanism of the soil. And this is very important to investigate through the geotechnical drillings, and therefore we can plan the improvement and strengthening of the soil. So I want to thank you for your attention, and I want to close this presentation and lecture with very, for me, inspirative quote, and it says, "The quality of our work is precisely in the simplicity of the ideas that inspired it." Again, assessment when it comes to heritage building is everything, and once you assess it thoroughly, therefore everything afterwards will be easy to plan. Thank you, and if you have some questions, I'm open to it.
Thank you very much, Mr. Pojatina, for a very interesting and detailed presentation. The examples you used were very, very relevant and very interesting. And also what I really liked, maybe even the most, was the fact that you were using a pencil and showing us the drawings. Drawing while you were presenting, it really helped us to get more involved on the very specific points that you were making. So I'm one more time, I'm using this opportunity to invite our listeners. If there are any questions, you may write them in the chat and question and answers. I see that there is one comment from Elena. She's saying a very interesting presentation. Thank you. Thank you, Elena, for your comment. If there is anyone else who would like to ask something or write a comment, we'll give you a few more seconds to do so. If not, I'm going to thank one more time to Mr. Pojatina. Thank you for joining. Thank you for your presentation, and thank you for your time, and of course for sharing your point of view and your knowledge. And it was a very lovely quote that you closed your presentation. Today.
Okay, so, thank you for invitation, and I was very glad to be the part of this kind of project. It's very important that we continue to discuss heritage buildings, especially the structural aspects, which were very often neglected during recent history.
Yeah, as we said, our final remarks, there is one question. Elena asked the question. She says, I would like to ask, in the temples, how are you putting cement when there are paintings on the walls?
Cement, the reinforced concrete was only used at the church tower, which did not have any paintings at all. So all other examples are strictly steel or FRCM elements or carbon fiber elements, and this kind of materials.
Okay, thank you. Yeah, okay, she says she's asking for the churches. Okay, yeah. Thank you. Thank you very much. As I can see, there are no more questions. Thank you once again. And as always, we'll keep in touch and include you in the rest of our projects and in the similar where your expertise is of great value. So thank you. And as the rest of participants can see, I shared my screen one more time with you to briefly discuss what I mentioned at the beginning. But before I discuss it, let me just finish by saying that this was our last presentation in this webinar series. And of course, thank you all very much for joining in our 4 webinars and for asking your questions and for being active in the Moodle platform. Let me briefly get back to what happens now after the online training is almost finished. As you know, today is the date to send in your 3rd assignment. Here on this slide, you can see the dates for the Croatian city workshops, because there are going to be 3 workshops in the 3 cities. First in Koprivnica on 27th and 28th of January, in Rijeka on 10th and 11th February, and finally in Zagreb in 1st and 2nd March. By the beginning of December, we will let you know your grades for the assignments that you sent in, and we will make the final list of participants who will join each of the city workshops. And one more addition, which is probably the most important one, is that we put in another week. So by 10th of November, you may send in your assignments, including the 3rd one, or if you missed some of the previous ones, or if you didn't send any assignments till now, but you know that assignments are important to be able to join for the city workshops, there is 1 extra week, so you can send in your assignments. We'll evaluate them until December and let you know who will join for the city workshops. The materials that are on the Moodle platform, they will be available until the next Sunday, 14th of November. So if you found them interesting and if you still didn't download them, please do so, because after that, you will not have the access to Moodle platform after that. And once you don't have the access to the Moodle platform, we will continue our communication via the emails, because before the city workshops begin, we will send you some preparatory material to go through, because in each of the city workshops, there will be 3 buildings that need to be renovated, and together in small groups, we will be tackling each cases. So in order to do so, we will send you some additional information for you to prepare regarding the buildings. And that's more or less it, unless you have some questions for what I just shared with you. We will shortly close this webinar. Thank you all again for joining for this whole program. We are still in contact via the Moodle platform. Please use this extra week to send in your assignments. For any questions, me and Agnieszka from Senzimir Foundation, of course, stand at your disposal. Thank you once again to Mr. Pojatina for our today's speaker. It was lovely to have you all for these past 4 webinars. And yeah, thank you for your time. We'll stay in touch and in contact, and see you all some other time. Bye.